All right. Let's talk a few minutes here about our directional derivatives and the gradient vector. Let me start, matter of fact, let me start with this gradient vector. It's going to be used here, of course, with directional derivatives, but it also has other applications and other contexts. We'll use it. And so definition-wise, our gradient vector, or notational, first of all, this will be what it looks like. Kind of looks like the delta sign, triangle sign, but tilted over. But f at a particular value, x, y, it's simply the partial derivatives partial derivative of f with respect to x at xy, and the partial derivative of f with respect to y of xy. Is our gradient, called the gradient vector. So it's just the partial derivatives put together in the form of a vector. And of course, if we use this notation, we could do that, and then we could also use the I and the J notation, and so it's two different ways of saying the same thing, or two different looks of the same thing, right? Okay, so it's just a vector. Now, this symbol right here, if you're not familiar with it, is del, Greek letter del. So del F is another way you can read that, the gradient vector, or del F. Okay. So if I have f of xy equals ln of x squared plus y squared, then what's the gradient vector f of f at the point 1, 2? Well, let's first of all just get it in general. The gradient vector here would be what? It's partial derivative with respect to x. So the first part of the vector is the partial derivative with respect to x. So that would be what? We've got ln, so it'd be 1 over x squared plus y squared. Times the derivative of the inside with respect to x would be 2x. And then then the same thing for the second part, except we're doing the partial derivative with respect to y. So that'd be 1 over x squared plus y squared. Be the derivative of the ln. Then the derivative inside with respect to y would be 2y. So it's just 2x over x squared plus y squared, comma 2y over x squared plus y squared. And so the specific vector they want here is at 1, 2. So that would just be, just substitute in. So it'd be, what, 2 over 1 squared plus 2 squared, so it'd be 2/5, comma 2 times the y, so that'd be 4/5. Okay? And so that's our so-called gradient vector at 1, 2 for this particular function. Now, where this comes up in this section is in with the idea here of what's called directional vector. Now, we found some directional vectors already, and directional derivatives, sorry. We found some directional derivatives already, and that is our partial derivatives, the partial derivative with respect to x and the partial derivative with respect to y. Those are directional in that the partial derivative with respect to x is in the direction of x, in the x direction, and then the partial derivative with respect to y is in the y direction. Now, that, however, can be extended, if you will. What if I want it in a different direction other than x and y? And so that's where directional derivatives come in. Directional derivatives are just derivatives in whatever direction you want. Okay, so let's say we've got this surface, whatever it is, sphere or paraboloid or whatever it is. Okay, it's just some surface here. Okay, and we found our directional derivatives in terms of the x and the y, partial derivative with respect to x, partial derivative. But say we wanted to know, what about like a tangent line in another direction? You know, we can find the tangent line in the x direction and the y direction with the partial derivatives, but what if we want to know the tangent line in a different direction, say, and the way we'll do it is with a unit tangent vector in the xy plane here, which I guess I should label my. So what if I didn't want it just specifically in the x or the y direction? What if I wanted it in, say, this direction here? And that's what we'll call our unit vector u. So what if I wanted a tangent line there, or in other words, I wanted a rate of change in that direction as opposed to just the x or the y direction? And so that's the idea of the directional derivative. And so, yeah, we just slice, what that does is that just kind of slices this surface here. You think of a tangent, a plane going through that particular unit vector. Well, that's going to hit our surface here and give you a tangent line in that direction. So instead of just going the x direction or the y direction, we can go a tangent in any direction we want. Okay. Now, what it turns out then happens is this directional derivative. If f is a differentiable function of x and y, then the directional derivative in the direction of u, unit vector u, and we'll just use A and B. They just use A and B for the general parts, components of that. So use the unit vector, parts A and B. Well, it's going to be this. Turns out, well, the notation is D for derivative. U, unit vector, is our direction of our function f of xy. Turns out that it's the partial derivative with respect to x at xy times a plus the partial derivative of f with respect to y at xy times b. So basically what it amounts to is, yeah, you do the a component times your partial derivative with respect to x, plus then the partial derivative with respect to y times the b component, and it basically works out from but as far as where that comes from is it does come from the limit definition. They go through it there in the book. It comes from the limit definition and works out to be partial derivative. So it's pretty nice. Now, a good way to remember this, or the way they go through this, is if we think about it here, this is a dot product of these two quantities. It's the partial derivative of x, comma, partial derivative of y, that vector, times the vector that would be AB. But what is this? That's the gradient vector times, that's our unit vector, right? And so that's a pretty nice way to remember what this directional derivative is. It's just the gradient vector times the dot product with the unit vector, the direction that you want. Not too bad. Okay? All right. So let's do a couple of those. Let's see what happens here. All right, so let's find the derivative. F of xy equals x squared plus xy. So find the derivative at P12, the point 12, in the direction of the unit vector. One over the square root of 2I plus 1 over square root of 2j. So that's just a vector 1 unit long in a different direction. Okay? All right. Well, what do we need? We need the directional derivative. And so we know that the directional derivative is the gradient vector dotted with the unit vector. Okay, so we need that gradient vector, don't we? And so the gradient is just the partial derivatives, right? Components are the partial derivatives, which in this case would be what? 2x plus y, okay. Partial derivative with respect to x would be 2x plus y. And then the partial of y, f with respect to y, well, that x is constant, so that would be 0. And so the derivative of that would be x, in terms of y. Okay? Now, we are wanting the derivative specifically at 1, 2. And so we can go ahead and evaluate our gradient at 1, 2. And so that would be 2 times 1 plus 2, comma 1. Okay, so that would be 4, 1. Yep. And so our directional derivative in the direction of u of f would be at 1, 2 would be, we take 4, 1 and dot that with unit vector 1 square root of 2, 1 over square root of 2. it'd be 4 over the square root of 2, so we just take that times that, plus then the 1 times 1 over the square root of 2. That's just 5 over square root of 2, isn't it? So that would be the derivative for this function in that direction. 1 over square root of 2 or 1 over square root of 2 is that'd just be a 45, right? So instead of going in the x or y direction, this is kind of going at a 45-degree angle, right? If you're talking about in the xy plane. So instead of going in the x or y direction, now we're going in that at 1, 2 anyway. So we're going at this 45-degree line in that direction. So along this surface, along that surface, that would be the slope, if you will. Something like that, yeah. Okay. Now, this, of course, could be extended to multiple variables other than x and y. What if we had an x, y, z function? Okay, so let's find the derivative of f x y z equals x cubed minus xy squared minus z at p110 in the direction of v equals 2I minus 3j plus 6k. All right, so we got a function in 3 variables here, but the same idea holds. Our directional derivative. Now we do need to be, for this to work, it needs to be in terms of a unit vector, u. But I still need to do the gradient of f dotted with that u. And so in this case, I do need a unit vector. But how do I get a unit vector out of just a? Yeah, you just take that vector and divide by the magnitude. And so we're going to take 2, negative 3, 6, and then divide it by the magnitude, which is just the square root of all the squares, right? 2 squared plus 4, negative 3 squared plus 6 squared. So, it's 2, negative 3, 6 divided by, square root of 49. So it'd be 2/7, negative 3/7, 6/7 would be my unit vector there. Now, what do you think about the gradient here? Well, since I'm in 3 variables, the gradient is just going to be the vector with the partial derivatives. F, the partial derivative of f with respect to x, the partial derivative of f with respect to y, partial with respect to z. Yeah, I'm just going to add one more component to that. All right, and so that would be, in this case, what? Partial derivative with respect to x, 3x squared minus y squared. Be the partial with respect to x. Partial with respect to y, well, that's 0. Be minus 2xy. And then the partial with respect to z would just be minus 1. right, so at 1, 1, 0, what do we got? So we got 3 minus 1. Yeah, okay, so that'd be 2. Negative 2 times 1 times 1, so that'd be negative 2. And then z is just a constant. Yeah, so it's negative 1. And so the derivative in the direction of u, f, would be the dot product of those two. So I take 2, negative 2, 1, negative 1, and then dot that with u, so it'd be 2/7, negative 3/7, 6/7. Yeah, so the dot product, just multiply components together and add them. 2 times 2/7 plus negative 2 times negative 3/7, and then negative 1 times 6/7. Add those up. 4/7, 6/7 minus 6. Hey, that works out. 4/7. Okay? Now, kind of mentioned it before, but re-emphasize here. Really, the partial derivative with respect to x and with respect to y is just kind of a special case of the directional derivative. It's just that if we're going in the x direction, if we want the derivative in just the x direction, then that would make our unit vector what? Well, the unit vector would be 1i plus 0j, right? And so if we take the directional derivative with respect to x in the unit director, that unit vector, so we've got the gradient of f times, or dotted with the unit vector there, what do we got? So this is partial derivative of f with respect to x, partial derivative. And then dotted with 1, 0. Yeah, just the partial derivative with respect to x, okay? So, yeah, so that's just a special case of partial derivative, just a special case of this directional derivative. And the same thing for the y. Yeah. Okay.